Today's lesson is going to be on something called implicit differentiation. Up until now, we've been finding derivatives for functions that have been y equals or f of x equals. But there are several times where functions are intermixed with the x and the y's, and you're not going to be able to separate them. So if you can't isolate your y in the original equation, you can still differentiate, but you're going to have to use something called implicit differentiation. So the implicit differentiation process is to differentiate both sides with respect to x, or the variable, but for the most part we're going to be using x. Collect all the terms with dy dx on one side of the equation, factor out dy dx, and solve for dy dx. So we're going to go through this process with, even though example 1 shows y squared equals x, and technically we could isolate y and get two equations, y equals rad x and y equals negative rad x, we're going to go ahead and just do this implicitly. So when you're taking the derivative of y squared, if it helps you for this first problem, I'm going to show you that this is the same as f of x quantity squared equals x. Now, this isn't a function of x, but I'm just using this to kind of show you the process. We've got a chain rule involved here. We've got something being squared on the left-hand side. So if I was to take derivative of that, you would bring the 2 down, and you would leave the inner layer alone, drop the power by 1, and then that outer layer of the 2 is gone. So if you go back now and you take the derivative of the inner layer and multiply them using the chain rule, you would have times f prime of x. And then that's it. On the right-hand side, the derivative of x is 1. Now, y squared equals x is not a function, so the proper way to do this is to just bring down the 2, leave the layer of y alone, it would be 2y to the first, and times the derivative of y. And I know everybody likes to use y prime because it's a little easier, but I'm going to show dy dx because there are going to be times where we're going to have y raised to a power, and it's difficult to tell the difference between a prime and a 1 when you're writing quickly, so I always use dy dx. And that's going to equal the derivative of the right-hand side, which is just 1. And in order to go ahead and find the derivative, you're just going to isolate this dy dx by dividing both sides by the 2y. And that would be the derivative. Notice it's not in terms of just x anymore. There might be y's involved. So we're going to go ahead and take a look at the next example. It says find the slope of the circle x squared plus y squared equals 25 at the point 3, negative 4. And we're going to go through the same process here. Slope indicates we should be finding the derivative. So we're going to do the derivative of x squared. You should get 2x. And the derivative of y squared, again, this is in terms of x, so we have to do the chain rule. The 2 is going to come down. We're going to leave the function, the y value, alone. It's not a function, but we're going to leave the y value alone, the dependent variable. And then we're going to take the derivative of that inner layer, just like we did with example 1. So the derivative of y is dy dx. And then the derivative of the right-hand side is 0. At any point when you're taking derivative and you're taking the derivative of anything with y, it's always going to be a dy dx involved. You're going to use that implicit piece. So now we can go ahead and plug in the point 3, negative 4. So 3 is our x value. Negative 4 is our y. And we're going to go ahead and simplify this, and we'll have negative 8 dy dx equals, this would have been a 6 on the left-hand side, but then I'm going to move it over to the other side. So you're going to end up with a negative 6. So if you solve for this, you're going to get dy dx equals 6 over 8, which reduces to 3 over 4. So that is the slope of the circle, x squared plus y squared equals 25 at the point 3, negative 4. Example 3 is asking you to show that the slope is defined at every point on the graph 2y equals x squared plus the sine of y. In order for a slope to be defined, it just means that when you have a derivative, the 0, you can't have a 0 in the denominator, you can't have negatives under square roots, everything like that. But the first step is to go ahead and find the slope or the derivative. So the derivative of 2y, well, the 2 is a constant multiple, so it's going to stay, and then the derivative of y is just dy dx. On the right-hand side, the derivative of x squared is 2x, and then the derivative of the sine of y is going to be the cosine of y, and that would take care of the outer layer, but then we've got the derivative of y, which is dy dx. Okay, so here we're going to actually go ahead and solve for dy dx. So isolate, get all the terms that have a dy dx over to one side of the equation. So I'm going to have 2 dy dx minus cosine y dy dx equals 2x. So if you factor out a dy dx, you would have 2 minus the cosine of y equals 2x. And then your final step, you would have dy dx equals 2x divided by 2 minus the cosine of y. Now, how do we prove that this slope is defined everywhere? Well, this denominator, as long as it does not equal 0, then that means that the overall slope is defined everywhere. And the definition, or the justification here, I'm going to put it off to the side, because 2 minus the cosine of y will never equal 0, right? And if you want to think about it, if you added over a cosine of y, cosine can only output values between -1 and 1, the cosine of an angle. So this is never going to equal 0, therefore this is always defined. All right, example 4, it says find the tangent and normal lines to the ellipse x squared minus xy plus y squared equals 7 at the point -1, 2. If you're feeling bold at this point, I would ask you to pause and see if you can find the derivative first, plug in the coordinate point, and then go ahead and write the equation of the tangent and the normal. This is where you can try your practice at it, so give it a shot. There will be a product rule involved. Okay, let's see if you chose to try this on your own. Let's see how you did. If you take the derivative of x squared, you would end up with 2x. This negative xy, this is technically, if you want to think about it as you'd be adding a negative x times y. That's one way to think about it. So this is a product rule. So the product rule says it's going to be the first, which is negative x, times the derivative of the second, which is dy dx, plus the second, which is y, times the derivative of the first, and the derivative of negative x is just -1. So that's that product. Plus the derivative of y squared is going to be 2 times y to the first. That's that outer layer, and then you have an implicit dy dx thrown in there, and the derivative of the right-hand side is 0. At this point, because it's giving you a specific x and y coordinate, you can go ahead and plug those in now. This is going to be 2 times -1, plus the opposite of -1, which is just 1, times dy dx, plus a y value of 2 times -1, so that's going to be a -2. Plus 2 times -2 times dy dx equals 0. Okay. So at this point, you're going to have a -2 plus dy dx minus 2, and this is going to be minus 4 dy dx equals 0. And we're going to have a -2 minus 2, so that's going to be a -4. And then we've got a dy dx here, and we've got a -4 dy dx here, so that's minus 3 dy dx. This equals 0. And if you want to go ahead and isolate this, you would add the 4 over and divide by -3. So you have dy dx, I'm going to leave a little bit of space, equals 4/3. Now, I'm going to show the proper notation here, and this is the derivative, dy dx, at the point -1, 2. I didn't do that during the process, but technically at this point over here, as soon as you plug in the coordinate point, you should have that notation on all of the dy dx's. you know, at this point, we're just trying to get used to it, so I'm not going to get bogged down with all the notation, but that is the proper notation to show the derivative at that coordinate point. Now to find the tangent and the normal lines, we have the point, it's -1, 2, and we have the slope. So for the tangent line, you're going to have y minus 2 equals 4/3 times x plus 1. And then for the normal line, point is the same. The only thing that changes, you do an opposite reciprocal slope. And that's it for that problem. Example 5 we're going to do, and then I'm sure if you have any questions, make sure that you ask me in class. This is the notation for the second derivative. The process is the same as finding the first derivative, so let's go through that first. The derivative of 2x cubed is going to be 6x squared minus, and we've got a chain rule here. This is going to be 6y to the first times dy dx. And then on the right-hand side, we'll have a derivative of 0. I'm trying to isolate dy dx, so the first thing I'm going to do is I'm going to add over the 6y dy dx. And I'm going to divide both sides by the 6y. So you'll have 6x squared over 6y equals dy dx. And you can cancel out those 6's. So you have an equation for your first derivative. Now, if you take the derivative again, so we have dy dx equals x squared over y. Now if you take the derivative again, you'll have the second derivative. So if you take the derivative of dy dx, you'll have d squared y dx squared equals, and now you're going to have to do a quotient rule. So low is y, d high is 2x, minus high, and then d low, but d low is dy dx. Sounds like I'm speaking another language right now. Some of you guys are like, you are. The only thing that you have to do before this is a proper answer is we can't have dy dx as a part of our second derivative. So I'm going to do this in a different color because we know what dy dx is. Dy dx is x squared over y. We're going to substitute that in here, and that's going to become our final answer then. So you're going to have d squared y dx squared is going to equal 2xy. I'm just kind of cleaning that part up a little bit. Minus x squared times x squared over y all over y squared for your response, and you are done. And that's the implicit differentiation. So again, there's only one difference, and that's anytime you're taking the derivative of y, you're going to have a dy dx involved as a part of the implicit piece. So I hope you enjoyed. See you tomorrow. Bye.